Okay, so this is our AP Chemistry Chapter 4 lesson video, Part 4. And so we're on our last section, Section 4.6. And in this section, again, a lot of this should be kind of review from honors. We're just going to kind of merge 2 units from honors. So we're still going to focus a little bit on solutions and molarity and things like that, but we're also going to head into titrations, which came from our acids and bases unit. Okay, so you can use molar mass and molarity to solve stoichiometry problems. Okay, so we're also going to kind of bridge that gap into stoichiometry. So that's the thing that you have to get used to in AP, is everything is not a separate category. They're all intertwined and they all work together. Okay, so you've got to learn to kind of start bridging the gaps in between the units and realize it's just all one continuous topic. So let's go ahead and jump in with a problem. So it says, how many grams of calcium hydroxide are needed to neutralize 25 milliliters of 0.1 molar nitric acid? Okay, so the first thing that you need to understand is when we're talking about neutralizing, what we're talking about is a hydrogen from an acid combining with a hydroxide from a base to make water. Okay, so for every 1 H plus, I need 1 OH minus. So whenever it talks about neutralizing, that's what I need you to think of. Okay, so it says how many grams of calcium hydroxide are needed to neutralize 25 milliliters of 0.1 molar HNO3. Well, we remember from stoichiometry, the only way to compare 2 different substances is through moles. Okay, because we need to get to that mole ratio. All right, so I know how many milliliters, I know my molarity, so I can use my molarity formula to solve for moles. Okay, so again, I'm not going to keep showing you how to rearrange it. Well, I guess for this video, I'll show you once. So molarity is moles per liter. So if I need to solve for moles, I just multiply both sides by liters. So moles is molarity times liters. Okay, so I'm not going to show you that again in this video. Trust me, this video is going to get kind of long. There's a lot of stuff going on. Okay, so you're going to have to kind of be able to follow and not have me show you the same things over and over again. Alright, so my molarity is 0.1, and my liters, remember we're going to have to change this to liters, so 1, 2, 3, so it becomes 0.025 liters. So y'all remember, 3 places to the left. Don't just put it in the front of the number necessarily. Okay, you got to go 3 places. So once I multiply, I get 0.0025 moles. And this volume and molarity went with HNO3. Okay, so that's how many moles of HNO3 I need to neutralize with my calcium hydroxide. Okay, so now this is where we're going to kind of use our mole ratio. Okay, so I start with my moles. So 0.0025 moles of nitric acid. And so now I need to look at what happens in a neutralization. Well, every nitric acid molecule is going to give 1 H plus. Every calcium hydroxide will give 2 hydroxides. So in other words, one of these can neutralize 2 of these, okay? Because one of these will make 2 hydroxides, so it can neutralize 2 of my acids. Okay, so I put my acid on bottom because I'm going to follow my golden rule. So 2 molecules of my nitric acid can be neutralized by 1 of my calcium hydroxide. Okay, and so we can make that into a mole ratio. Because remember, we don't deal with 1 molecule at a time in chemistry usually. We're talking about moles. All right, so I know 1 mole of calcium hydroxide can neutralize 2 moles of nitric acid because each calcium hydroxide is going to make 2 hydroxides. Alright, so once I divide by 2, I end up getting, where am I looking? Oh, sorry, we're not going to divide by 2 just yet because that will give me moles of calcium hydroxide, but what did it ask me for? It asked me for grams. So instead of stopping and doing another problem, let's just keep going. Alright, so I need to go from moles to grams using molar mass. So when I add up calcium hydroxide, I end up getting about 74 grams. So I can see that 1 mole of calcium hydroxide, following that golden rule, equals 74 grams of calcium hydroxide. So I multiply and divide, and I end up getting about 0.0925 grams of calcium hydroxide. So that's how much calcium hydroxide I would need to neutralize the acid in this solution. All right, so a lot of stuff going on here. Like I said, we're just kind of comparing some molarity stuff with some acid and base titration information. Okay, so remember, for acid-base titrations, you've got to focus on moles, so you can do that mole ratio for the neutralization portion. All right, so maybe pause it, try this one on your own, and then I'll assume you've done that. We'll look at it together. I'm not gonna lie, there's a lot of math in this video, so good thing I like it. All right, so it says how many grams of sodium hydroxide are needed to neutralize 20 milliliters of 0.5 molar sulfuric acid solution. Okay, so again, I need to get to moles. I know my milliliters, I know my molarity, and I know how to rearrange my formula. Moles is molarity times liters. So my molarity is 0.15, and I can change this to liters by going 1, 2, 3. So it's 0.02 liters. And so once I multiply for that, I ended up getting 0.003 moles of sulfuric acid. Okay, and I know it's the sulfuric acid because I'm using the volume and the molarity of the sulfuric acid. All right, but I'm trying to get to NaOH, so I know the only way to change substance is through my mole ratio. So I'm trying to neutralize 0.003 moles of my acid. So now we need to look at, remember, one H can neutralize one OH. NaOH has one OH. H2SO4 has two H's. So in other words, one of my acid can neutralize two of my base, because one of my acids is going to have two H's. So it can neutralize two OHs. Okay, so one of my acids, I'll put one of my H2SO4 on bottom, can neutralize two of my base, my NaOH. Alright, but I'm going to keep going because it doesn't ask me how many moles, it asks me how many grams of NaOH. So I use my molar mass. NaOH, when you add up, is about 40 grams. So 1 mole of NaOH is about 40 grams of NaOH. So once I multiply across the top, I end up getting about 0.24 grams NaOH. So that is how much base I would need to add to neutralize all of that acid. Alright, so hopefully you got that one right. Okay, if you haven't already tried one, at least pause it and try part B. So it says how many liters of 0.5 molar HCl are needed to react completely with 0.1 moles of lead-2 nitrate, forming a precipitate of PbCl2. Okay, so in this case, instead of doing a neutralization reaction, we're trying to form a precipitate between our lead and our chloride ions. That's what we're trying to do here. Okay, so if you notice, I have 0.1 moles of lead-2 nitrate, and I'm looking for how many liters of 0.5 molar HCl. So in other words, I need to figure out how many moles of HCl I need so I can use that formula. So I'm going to start with my 0.1 moles of the lead-2 nitrate. So that's what I'm going to start with. And so one thing that's helpful sometimes, especially when you're trying to do your mole ratio, is if you're not sure, write the reaction. So what we have happening here is we have lead ion reacting with chloride ion to make lead-2 chloride. So of course I'm going to need 2 chloride ions. Okay, so that can help you figure out the mole ratio for this one. So I know for every 1 of my lead, I'm going to need 2 of my chlorides. Alright, so I can say, okay, well, for every 1 lead nitrate, or 1 mole of lead nitrate, I'm going to need 2 moles of my hydrochloric acid, because of course, we need it to be PbCl2, so I'm going to need double the Cl. Alright, so once I get that, I realize that means I am going to need 0.2 moles of HCl. Once I know how many moles of HCl, I know my molarity, and so I can solve for liters. And so in a previous video, I already showed you how liters is moles over molarity. So then I just plug in. So 0.2 moles over my molarity, which is 0.5, gives me 0.4 liters. So that's how many liters of this concentration of acid I would need to combine with 0.1 mole of lead-2 nitrate in order to precipitate all of the lead. Alright, so hopefully you got those right, and so just notice that it doesn't matter if it's a neutralization reaction or a precipitate reaction. They both work the same way. Okay, you just got to figure out that mole ratio. If writing the reaction helps, write the reaction. Alright, so titrations. To determine the concentration of a particular solute in a solution, chemists often carry out a titration, which involves combining a sample of the solution with a reagent solution of known concentration called the standard. So down here we have our unknown concentration or our unknown solution. And up here in our burette, we have our known solution. So we should know everything about what's in the burette. Something down here we don't know. Could be like the concentration, something like that. So that's what's happening in a titration. And so what we do is we can add the known until something happens. Be it a precipitate, be it a color change because you've added an indicator. So the point at which stoichiometrically equivalent quantities are brought together is known as the equivalence point. So in acid-base titrations, dyes known as acid-base indicators are used to identify the equivalence point. The color change of the indicator signals the end point of the titration, which usually coincides very nearly with the equivalence point. So the equivalence point happens when you've added equal amounts of, stoichiometrically equal amounts of your acid and your base. That's known as equivalence point. The end point is when your indicator changes color. So if your equivalence point is going to be at a pH of 7, you don't want an indicator that changes color at a pH of 3. Okay, so you've got to pick the correct indicator based on what titration you're doing. A common indicator used in titrations is phenolphthalein. It is clear or colorless in acidic and neutral conditions, and once it goes slightly basic, that's when it becomes pink. But not all titrations warrant a pH change at this point, and so phenolphthalein might not be the best indicator. So there's lots of different indicators you can choose from. So let's look at our sample exercise. So it says how many grams of chloride ion are in a sample of the water if 20.2 milliliters of 0.1 molar Ag or silver ion is needed to react with all of the chloride in the sample. Okay, so we have silver ions and chloride ions making silver chloride, silver 1 chloride. Okay, so it tells me my milliliters and molarity of my silver, so I can go ahead and get to moles. Okay, so remember, moles is my molarity times my liters. So my molarity is 0.1. My liters, remember, 1, 2, 3, don't forget to move that decimal, is 0.0202. Okay, so once I multiply for that, I got 0.00202 moles for my silver. Okay, so I can clearly see, without doing the math, that this is a 1-to-1 ratio. Like for every silver, I need a chloride. All right, but it doesn't ask me for moles of chloride, it asks me for grams. So I can see that this is also going to equal my chloride because it's just a 1-to-1 ratio. So I take my moles, which I've now changed to chloride because I realize it's just 1-to-1, but I need to get to grams. So chlorine is about 35 grams per mole. So I'll put my 1 mole, 35 grams. And don't worry about the fact that it's the chloride ion instead of the chlorine atom. Remember, electrons don't change the atomic mass of an element. All right, so my moles cancel. So once I multiply by 35, I got 0.0707 grams of my chloride ion. So that's how much chloride I would need to precipitate all of my silver ion. All right, so then it says, if the sample has a mass of 10 grams, what percent of the chloride ion does it contain? So don't let something like this throw you off. A percentage is a part per the whole thing times 100. So what part am I talking about? I'm talking about chloride ion. Do I know how much chloride ion? Yes, I just calculated it. So my part is my chloride ion. And then we do over the whole thing. Well, they said the sample has a mass of 10 grams, so that would be the whole thing. So in other words, we're looking for our percent of chloride. And then, of course, to make it a percentage, we multiply by 100. And so I ended up getting 0.707% chloride ion. Okay, so don't let them throw in a percent composition problem in with something else, throw you off. You know a percentage is part per whole times 100. And so that's what it is, chloride per the whole sample times 100. All right, so you saw me do one. So maybe pause the video and you try the next one real quick. All right, I'll assume you've done that and we'll go ahead and start on this one together. All right, so it says a solution that contains iron 2 ion is titrated with 47.2 milliliters of 0.0224 molar permanganate. How many moles of permanganate were added to this solution? So it's asking me about permanganate. It told me about permanganate. So right now, I don't even need to worry about the iron. Okay, so I know that to get moles, I can do molarity times liters. So my molarity is the 0.0224 molar, and my liters is, remember, 1, 2, 3, don't forget to move it over 3.04720 liters. Okay, so once I multiply that, I end up getting about 1.06 times 10 to the negative 3 moles of the permanganate ion. Okay, so notice in part A, I didn't need this reaction. I didn't need anything to do with iron. Okay, in part A, it's just asking how many moles of permanganate were added. So that's what I calculated. Then it says how many moles of iron +2 were in the sample. Okay, so in other words, my permanganate and my iron is what we're looking at. So I can see that 5 moles of iron requires 1 mole of permanganate. So I can see my mole ratio. We know how many moles of permanganate, so I just bring that down. So 1.06 times 10 to the negative 3 moles of permanganate. And then I just use my mole ratio. 1 mole of permanganate is 5 moles of iron. Okay, so I just take my answer and multiply it by 5. So 5.3 times 10 to the negative 3 moles of iron. And that's all you have to do, okay? We're just combining molarity with mole ratio, stoichiometry, titrations, whatever. They're all the same. All right, now I can see on my paper that there's a part C and a part D, so looks like I need to pull this number. So I'm going to bring this number to the next slide with us. Okay, so if you haven't tried part C and D, maybe pause the video and try part C and D real quick. Then I'll assume you've done that. So it says how many grams of iron were in the sample. Okay, so I had to pull the moles of iron from my previous one, which was 5.3 times 10 to the negative 3 moles of iron. Okay, so I'm just going to grams. Just use a molar mass. 1 mole of iron is, let me not forget my 2 plus, because it is an ion, is 56 grams. So remember, don't let the ion throw you off. You use the same molar mass off the periodic table. So once I multiply by 56, I get 0.3 grams of iron. Just like that. All right, so now this one's similar to the part B on mine. It says if the sample had a mass of 0.889 grams, what is the percentage of iron? Okay, so in this case, we're looking for our iron. So remember, it's the part, so just the iron, which we just calculated was 0.3 grams, over the whole, which they just told me is 0.8890 grams, times 100 to make it a percentage instead of a decimal. All right, so once I do that, I ended up getting about 33.7% iron. just like that. All right, so hopefully you got some of that right. Yours was kind of just broken up into a few more steps than mine was. That's why you had part A through D. They were just kind of breaking it up to kind of guide you through what you should have been doing. All right. So, another sample exercise. It says, one commercial method used to peel potatoes is to soak them in a solution of sodium hydroxide for a short time. Remove them from the sodium hydroxide and then spray off the peel. The concentration of sodium hydroxide normally is in the range between 3 to 6 molar. The sodium hydroxide is analyzed periodically. In one such analysis, 45.7 milliliters of 0.5 molar sulfuric acid is required to neutralize 20 milliliters of the sodium hydroxide solution. What's the concentration? Okay, so I know how much sodium hydroxide. I need to know how many moles because I'm trying to get concentration. But I know the molarity and the volume of the sulfuric acid. So first I need to figure out how many moles of sulfuric acid were used. Okay, so I know that moles is molarity times liters. So my molarity of sulfuric acid is 0.5. And remember, I got to change this to milliliter. To liters. 1, 2, 3. So it becomes 0.0457 liters. So once I do that, I get I'm looking at the wrong question. Okay, there it is, 0.0. Ooh, that would have made a lot of sense to put the wrong answer up here. I get 0.023 moles of sulfuric acid. So next, of course, though, I need to get to sodium hydroxide. Okay, so I need to use my mole ratio. Here, I'll just continue right here. All right, so I can see that 1 mole of sodium hydroxide, let me start with the other way. It's easier for me to describe it the other way. 1 mole of sulfuric acid can neutralize 2 moles of sodium hydroxide because sulfuric acid has 2 hydrogens. Sodium hydroxide only has 1 hydroxide. Okay, so 1 sulfuric acid can neutralize 2 sodium hydroxide. So 1 mole of my sulfuric acid, I was going to start with 1 mole of sodium hydroxide is half a mole, but I felt like that might confuse some of you. Can neutralize 2 moles of my sodium hydroxide. So once I multiply by 2, I end up getting 0.046 moles of sodium hydroxide. Now that I know my moles and I know my volume, I now can calculate my molarity. Okay, so molarity is mole per liter. So we know how many moles of sodium hydroxide, 0.046. And we know we had 20 milliliters, so that's 0.02 liters. So once I do my math here, if I could quit trying to look at the wrong one, I keep going down and it's the top one. I get about 2.3 molar. So would this sodium hydroxide be safe to use in this process? Well, they said they like it between 3 and 6. So in other words, it sounds like they need to up the concentration a little bit, or it might not do as good a job with the peeling. All right, so hopefully that one wasn't too bad. So let's let you try one. Okay, so maybe pause it, try this one, then we'll look at it together. So it says, what is the molarity of sodium hydroxide solution if 48 milliliters is needed to neutralize 35 milliliters of 0.144 molar sulfuric acid? Okay, so we have the same neutralization happening, sodium hydroxide and sulfuric acid, so hopefully yours will be very similar to mine. So the first thing I need to do is start by figuring out how many moles of sulfuric acid I have by doing molarity times liters. So my molarity is 0.144. My liters is 123.035. So for my moles of sulfuric acid, I end up getting 0.00504 moles. Whoop, that says water, not sulfuric acid. That would be quite a different reaction. All right, so next I need to get to sodium hydroxide. So I start with my moles of sulfuric acid. And so like we said in the previous question, 1 mole of sulfuric acid, because it has 2 hydrogens, can neutralize 2 moles of NaOH, because it only has 1 hydroxide. So 1 mole of my acid can neutralize 2 moles of my base. So once I do that, I get 0.01008 moles of sodium hydroxide. All right, once I know that, I can figure out the molarity because it gave me the volume. So see, I have the moles, I have the volume. So molarity is moles per liter. So my moles is 0.01008. And my liters is, move it over 1, 2, 3, 0.048 liters. Okay, so I divide, and so for this one, I got 0.21 molarity. All right, so hopefully you got the same thing. Okay, so really it's all about kind of using molarity, using mole ratio, using molarity again. Be it, are you trying to figure out the volume or are you trying to figure out the concentration? But remember, the way we compare two different substances is through moles. Okay, we've got to go through that mole ratio at some point. All right, so sample integrative exercise. So this is where we kind of start pulling things together from different chapters. All right, so it says a sample, let's see, there's part A, B, and C. So I may need some of this information on part C. We'll see what happens. All right, so it says a sample of 70.5 milligrams of potassium phosphate is added to 15 milliliters of 0.05 molar silver nitrate, resulting in the formation of a precipitate. Okay, so in other words, we are mixing potassium phosphate with silver nitrate, so our precipitate should be silver phosphate. Write the molecular equation for the reaction. Okay, well, let's start with that. So we have potassium phosphate. So potassium is K, positive 1. Phosphate is PO4, negative 3. We need 3 Ks, and it is aqueous. Oh, let's see, 70, it didn't tell me if it's aqueous or not. If they're doing milligrams, most likely it's a solid. It's mixed with silver nitrate. So silver is Ag, positive, nitrate's NO3, negative. And it results in the formation of a precipitate. So this is just double displacement. So remember, I'm just going to swap my two positives. So K is now going to be with NO3, but remember, it only has the 3 here because it was with phosphate. It's not with phosphate anymore. So K positive, NO3 negative, that cancels. And so then we have our silver bonding with phosphate. So silver is positive 1, phosphate's negative 3, so I need 3 silver to balance that out. And so then next we are going to balance our reaction. So I have 3 Ks, here I only have 1, so I need a 3. I have a phosphate, 1 silver, 3 silver, so I need a 3. 3 nitrates, 3 nitrates, just like that. All right. So, next part. And I could go through and put my states of matter too. Like I said, because they didn't specify it's a solution, this could be solid or aqueous. We're really not sure based on what it's told me in the problem. Then we know this is a solution, so we know this would be aqueous. And then we know nitrates and alkali metals are soluble, so this would be aqueous. And then we know that phosphates tend to be insoluble, so this would be our precipitate. So really the only one we would have to question is this. Are we adding solid potassium phosphate, which like I said is what it makes it seem like since we have milligrams, or are we adding a solution? All right, so part B says, what is the limiting reagent in the reaction? All right, so going back to stoichiometry, limiting reagents. Okay, so we have our reaction here. And let's see, I'm going to go to our precipitate because I would assume that's what we'll be most interested in. Okay, so I'm going to start with my 70.5 milligrams of potassium phosphate and figure out how much of my precipitate I would form. And then I'll start with my 15 milliliters of 0.05 molar silver nitrate and figure out how much of my precipitate I could form. And then, of course, limiting is the lowest, so I would pick the lowest amount. All right, so I'm going to do my potassium phosphate first. So the important thing to note is I have 70.5 milligrams of the potassium phosphate. Okay, I'm not starting with grams. So 1,000 milligrams equals 1 gram. So first thing is I need to get to grams. Okay, once I get to grams, then I need to go to moles. Okay, so K3PO4, when you add that up, you should get about 212 grams. And that is 1 mole. So that was just me adding up molar mass. Alright, next I need to get from potassium phosphate to my precipitate. It's a 1-to-1 ratio. So 1 mole of K3PO4 is going to make 1 mole of Ag3PO4. Just like that. Alright, now it didn't specify what to go to, so I could stop at moles, but hang on, let me see what part C is real quick. Oh, I can just look on here. Oh, what's theoretical yield in grams? So since part C is already asking me for the yield in grams, I'm going to go ahead and go to grams. So now I need to add up the molar mass of Ag3PO4. So that's about 419 grams. So 1 mole of AgPO4, 3PO4, is 419 grams. So, I didn't cancel out my units. Once I multiply and divide across that, I get 0.14 grams of Ag3PO4. Now, of course, I don't know if the potassium phosphate is my limiting or not, because I don't know is this the greater amount or the lower amount that's going to be produced. So I won't know until I do my other one. Now, the other one has a trick. They didn't give me grams, they didn't give me moles, they didn't give me any of that to start with. But I can figure out moles using my molarity formula. Okay, so remember, moles is molarity times liters. So they gave me the molarity, 0.05. They gave me milliliters, so that's going to be 0.015 liters. And so once I multiply for that, I end up starting out with 7.5 times 10 to the negative 4 moles of silver nitrate. Okay, so that's actually where I'm going to start on my limiting reagents problem. So see, like I said, y'all, you have to be able to pull skills from different chapters and combine them together in the same problem. Okay, like giving you a stoichiometry problem but making you do molarity to get moles first shouldn't be a problem. Okay, so I already have moles now, so I can go directly to mole ratio. So 3 moles of silver nitrate makes 1 mole of the silver phosphate. Right, so I put my 3 moles silver nitrate on bottom. That's the 1 mole of silver phosphate on top. And then last step is, of course, to get to grams of silver phosphate. So we already know molar mass is 419, so I put my 1 mole silver phosphate on bottom and my 419 grams of silver phosphate on top. So then I just multiply and divide, and so for this one I get 0.105 grams of silver phosphate. Now notice this question didn't ask how much of my precipitate I can produce. It asked what is the limiting. So remember, a lot of you like to try to label these two things as limiting. That's not the way it works. Okay, the limiting reagent, you find the lower of the two numbers, so 0.105, and you look at what made the lower one. So my limiting reagent would be the silver nitrate. Now it didn't ask me for my excess reagent, and obviously it's just the other one, but just in case it did, I find my higher number, I go back to the front. That is my excess reagent, so K3PO4. Okay, so that's our answer for part B. Now I'm going to leave part B up here because in doing part B, we actually already did part C. Okay, so I'm going to erase part A though, and click. And part C says, calculate the theoretical yield in grams of the precipitate that forms. Well, I have my two amounts. What's the amount that we actually make? The lower of the two. So for part C, this would be my answer. 0.105 grams of my silver phosphate. So see, in doing part B, I just already did part C. So I did both of them together. All right, so hopefully that wasn't too overwhelming. Chapter 4 is kind of a lot. We kind of start, like I said, bridging the different units of honors chem. But overall, overall, chapter 4 should mainly be a review from Honors Chem. Okay, so hopefully this is kind of helping you start to piece things together, but it's also just helping you remember some things you might have forgotten since you have you for honors.